Okay, good. Okay. Okay, so let me start then. Okay, all right. So, okay, so right. Okay. So last time we showed, so we talked about the Lie derivative, right? So what was the Lie derivative? It was the following. You have two vector fields, x and y, and what you do is you look at a point P, you look at the integral curve of x passing through P, and then you look at the values of y at points along the integral curve. So you look at y at phi t of P, and then what you can do is, so the tangent spaces at P and at phi t of P, these are different vector spaces, right? But so it doesn't make sense to differentiate y phi tp directly with respect to t, because it takes values in different vector spaces for different values of t. But what you can do is you can use the flow of x to identify these two tangent spaces, because the map phi minus t is a diffeomorphism of the manifold which takes phi t of P back to P. So if I apply the derivative of a diffeomorphism, that is an isomorphism between tangent spaces. So d phi minus t is an isomorphism between the tangent space at phi t of P and the tangent space at P. So I can apply d phi minus t to y at phi t of P. So I get, now I have two tangent vectors in the same tangent space. So then I can take their difference and then divide by t and let t tend to 0. Okay, so this was the Lie derivative. Okay, so here's the formula. It's d phi minus t of y phi t of P minus y of P. So both of these are tangent vectors in the same tangent space at P. Then you divide by t and let t tend to 0. Okay. And then what we showed is the Lie bracket equals the Lie derivative, sorry, equals the Lie bracket. Okay. So, I mean, this proof shows that this limit exists, and it defines a smooth vector field, because we know the Lie bracket of two smooth vector fields is a smooth vector field. Okay, so this is where we finished last time. So any questions about this so far? Okay, so I think one of you mentioned last time, what happens if the Lie derivative is 0? So we'll see that amounts to saying that the flows of x and y commute. So we'll come to the proof of that. So first, let's look at a vector field which is invariant under a diffeomorphism of the manifold. So suppose f from the manifold M2 itself is a diffeomorphism, and x is a smooth vector field on M. Then x is f invariant. So that means that df at P, it maps x at P to x at f of P. Okay. So recall that if f is a diffeomorphism, then df at P is an isomorphism between the tangent spaces at P and at f of P. So what we require, we say that x is f invariant if df maps the tangent vector of x at P to the tangent vector of x at f of P. Okay. So to give you an example of a f invariant vector field, if we look at this picture, let me see where it is. Yeah, if you look at this picture here, for example, in R2, you take, say, y to be the radial vector field. So y of p is equal to the vector p. You think of p as a vector in R2. So you look at this radial vector field, which this is the picture of the radial vector field. And then you take your diffeomorphism f to be a rotation. Okay. You take your diffeomorphism f to be a rotation. Then you can see the derivative of the rotation. It maps the tangent vector of y at p to the tangent vector of y at f of p. Is this okay? So this so to say that a vector field is f invariant. Okay. So to say that a vector field is f invariant means that
টাওয়ার আসবে না না এই ঘরে টাওয়ার আসছে না এই ঘরে পেতে দাও না পায়ের তলায় ধুলাম অবশ্য না পরে পরিষ্কার
Okay, should I continue? Okay, so all right, so you can see in this picture the radial vector field y is invariant under the diffeomorphism, which is rotation around the origin, any rotation around the origin. Okay, so that means that f is a symmetry of the vector field. Okay, so you think of if you think of the diffeomorphisms which leave a vector field invariant, then they form a group which you can think of as the group of symmetries of the vector field. Okay, so so let's come back to this proposition. So what the proposition says is that a vector field x is f invariant if and only if the diffeomorphism f commutes with the flow of the vector field. Okay, so f composed phi t is phi t composed f for all t small enough. I mean, the vector field need not be complete. So then phi t is only defined locally for t small. So this should hold for t small near every point. Okay. So is the statement clear? So you can see that in this picture. So in this picture, our vector field, the radial vector field is invariant under rotation, and the flow of the radial vector field, it moves along the radial lines through the origin, along rays through the origin. So the flow of the vector field will be, so I've already used phi t for the rotation here, but the flow of the vector field will be p maps to e to the t times p, right? It will be a scaling by a factor of e to the t. And that commutes with rotation, right? Because rotations and scalings in R2, they commute, right? Rotations and scalings commute. So that's what we see in general in this proposition, that the vector field x is f invariant if and only if the flow of x commutes with the diffeomorphism f. Okay, so let's prove this. So first, the forward implication. So suppose that x is f invariant, then we want to show that f commutes with the flow. So what we do is we look at the curve f composed with phi t of p. And what we will do is we will show that this is an integral curve of x. So we look at its derivative. So its tangent vector. So by the chain rule, ddt of f of phi t of p will be df at the point phi t of p applied to the tangent vector of the curve phi t of p And now what is the tangent vector of the curve phi t of p? So it is an integral curve of x. So that means the derivative of this will be nothing but x at the point phi t of p, right? So this will become df at phi t of p applied to x at phi t of p. And now we use the fact that x is f invariant. So by the f invariance, this will be x at the point f of phi t of p, right? Is this clear? Yes. So what does this mean? This means the tangent vector to the curve f composed phi t of p is equal to the value of the vector field x at the point on the curve f composed phi t of p. In other words, this curve t maps to f of phi t of p. This is an integral curve of x, right? This is an integral curve of x. And we know what the integral curves of x are. They are given by applying phi t to the initial position of the curve. So what is the initial position of the curve? When t is equal to 0, then this is just f of p, right? Because phi 0 is the identity. So this is the integral curve of x with initial condition f of p. So therefore, this curve must be the same as phi t applied to f of p, right? That is the integral curve of x with initial condition f of p. And so therefore, we get that f composed with phi t of p is equal to phi t of f of p. Is this clear?
Yes.
Yes? All right. So now the other direction is also straightforward. So suppose that the flow of x commutes with the diffeomorphism f, then we want to show that dfp of xp is equal to x at f of p. So we use the fact that xp, this is the derivative of the curve phi t of p, and dfp of xp, therefore, I can write as ddt at t equal to 0 of f of phi tp, right? By the chain rule, right? Okay. And
Yes.
okay. And so what is this? Now we use the fact that f and phi t commute. So this is the same as ddt at t equal to 0 of phi t of f of p. And now we use the fact that phi t of f of p, this is the integral curve of x with initial value f of p. So when I take its derivative at time 0, I'll just get x at f of p, right? And so therefore, df of p of xp is equal to x of fp. And so that means that x is f invariant. Okay. So is the proof clear?
Yes.
Okay. All right. So now we can show what I think Utshab asked in the previous class, that when is the Lie bracket 0 or the Lie derivative 0? So that is if and only if the flows of x and y commute. Okay, so that's what this proposition says. Bracket xy is 0 if and only if the flows of xy commute. So let's prove this. So let phi t be the flow of x and psi s is the flow of y. Okay. So first we'll show that if the flows commute, then the bracket is 0. Okay, so this is the backward implication. So then we're given that phi t composed with psi s is equal to psi s composed with phi t for all st. Right? The flows are given to commute. Now, by the previous proposition, this means that phi t, because it commutes with the flow of y, therefore phi t leaves y invariant, right? This means that y is phi t invariant. Yes? By the previous proposition, y is phi t invariant for all t. So now we use the fact that the Lie bracket I can write as the Lie derivative. So bracket xy is equal to Lxy, the Lie derivative. And now the Lie derivative in the definition, this is limit t tends to 0, d phi minus t, y at phi t of p minus y at p divided by t, right? And because we've just observed that y is phi t invariant, that means that that's true for all t. So in particular for minus t also this is true. So this means that d phi minus t will take y at phi t of p to the tangent vector y at phi minus t of phi t of p, right? So this from here to here, this is by the phi t invariance of y, all right? And phi minus t of phi t of p by the group law, this is equal to p, right? Phi minus t and phi t are inverses of each other. And so that this becomes yp minus yp, so that's 0. Okay, so the Lie derivative is 0, therefore the Lie bracket is 0. Is this all right? Yes? Any questions? This is fine?
Yes, sir.
Okay, all right. Okay. So let's prove now the forward implication. So we're given that the Lie bracket is 0. We want to show that the flows of x and y commute. Okay. So what can we do? So what we do is the following. We want to show that if the Lie bracket is 0, then what we will show is that y will be phi t invariant. Okay, that's what we will show, where phi t is the flow of x. So to do that, we look at these tangent vectors that occur in the Lie derivative, d phi minus t of y at phi t of p. Okay, so these are, notice that these are all tangent vectors at the point P. So they lie in the same vector space. So this is a curve in the vector space TPM. Therefore, it's a curve in the same vector space. So we can differentiate it, take its time derivative ddt. All right. So we take ddt of this. And now what I'm going to do is write ddt of this at time t. I'll write it as dds at time s equal to 0 of this evaluated at t plus s. Okay. So when I do that, this becomes a limit s tending to 0, 1 over s d phi minus t. And then I use the group law that phi of minus t plus s is phi minus t minus s. And by the chain rule, I mean, it's phi minus t composed with phi minus s. So by the chain rule, the derivative of that is d phi minus t composed with d phi minus s. Okay. And then I have y at the point phi t plus s of p. So that will become y at phi s of phi t of p. And then minus y at phi t of p. All right. Is this okay? So this derivative ddt of this is equal to this limit s tending to 0. And now this d phi minus t is a linear map. So this 1 by s I can take inside, right? I can take the 1 by s inside. And when I do that, then inside what I get is the definition of the Lie derivative at the point phi t of p, right? So when I take limit s tending to 0, the inside term, it converges to the Lie derivative Lxy at the point phi t of p. Okay, and so since the inside term converges, I mean, d phi minus t is a continuous linear map. So therefore, this converges to d phi minus t of Lxy of phi t of p. But we're given that the Lie bracket is 0. That's our hypothesis. So that means the Lie derivative is 0. So therefore, this Lxy is 0 at phi t of p, and so this is 0. So that means the derivative of this curve is 0. ddt of this d phi minus t y phi t of p, this is identically 0. Therefore, this is a constant curve, right? So that means that d phi minus t of y phi t of p, this is constant equal to yp. So now what I can do is I can apply d phi t to both sides of this equality. And then what I'll get is that y at phi t of p is equal to d phi t of yp. Is that clear?
Yes.
Right? So this means
Yes.
what? Y at phi t of p is equal to d phi t of yp. This means that y is invariant under phi t, right? Y is phi t invariant. So therefore, y is invariant under phi t for all t. This is true for all t. But what does that mean? That means that the flow of y commutes with phi t for all t, right? The flow of y commutes with phi t for all t. This is by the previous proposition. And that proves what we want, right? So that means the flows of y and x commute. Okay, phi t was the flow of x, and we've just shown that the flow of y commutes with phi t. So therefore, the flows of y and x commute. Is this all right?
Yes.
Okay. All right. So the Lie bracket, as I tried to mention in the previous class, at the end, we have this interpretation of the Lie bracket as an infinitesimal commutator of flows. So you take a point P, you flow by the first flow for time square root t, then you flow by the second flow for time square root t, then you flow by the inverse of the first flow for time square root t, and then by the inverse of the second flow for time square root t. Then you almost close up. Okay, so you get a curve which depends on t, and at time t equal to 0, this is equal to p. So you take its derivative at time t equal to 0. That will give you a tangent vector at p, because it's a curve which passes through p at time t equal to 0. And so you take its derivative at time t equal to 0, and that will give you a tangent vector at p. And that tangent vector turns out to be nothing but the Lie bracket of xy at p. Okay. So it measures this little gap where the square fails to close up. All right, it measures this little gap. Okay. So I mean, so geometrically, what this proposition is saying, I mean, the Lie bracket, you can think of it as an infinitesimal commutator, right? It's like an infinitesimal commutator. So saying that the Lie bracket is 0 means that for very small times, infinitely small times, the flows of x and y commute. And then what we are proving is that if the flows commute infinitesimally, that is the Lie bracket is 0, then they actually commute for all time. All right. That's what this proposition means intuitively, that commuting for infinitesimal times means that you commute actually for all times. It's equivalent to commuting for all times. All right. So does this make sense? Any questions? Yes, go ahead. Yes.
How that
I'm sorry, Bappa, your sound is not clear. I can't hear you exactly. Can you try speaking again? Okay, you've written in the chat. All right. You'll ask in the end. Okay, fine. Okay. All right. Okay, so let's continue then. So the next main topic, which will be the topic for the next couple of lectures, is what's called covariant derivatives. Okay, so we will introduce this topic gradually. So first of all, what is the covariant derivative of a vector field in the simplest manifold, which is Rn? Okay, so in Rn, this is an easy thing to define. Well, I mean, when I say covariant derivative of a vector field, the point is that, see, vector fields, if I look at a vector field on a manifold, then at different points, the values of the vector field lie in different tangent spaces, which are different vector spaces, right? So it doesn't make sense a priori to define the derivative of a vector field along a curve, right? If I have a curve in the manifold, I want to differentiate the vector field along that curve. It doesn't make sense a priori because the vector field takes values along at different points along the curve. It takes values in different tangent spaces. Okay, but so what a covariant derivative is a way of differentiating vector fields along curves, which will give a way of identifying tangent spaces. Okay, so at different points. But if we are working in Rn, then this is there's no need to do this. In Rn, there is a natural covariant derivative because all the tangent spaces to Rn are identified naturally, canonically, with Rn itself, right? This we've seen. In Rn, at each point, the tangent space is naturally identified with Rn itself. So all the tangent spaces are naturally identified. And so a vector field on Rn, we can think of as taking values in the same vector space at all points, which is Rn, right? So that's why when we teach vector fields and ODEs in multivariable calculus in Rn, we just write a vector field as a map from Rn to Rn itself, right? So the left-hand side, the domain Rn is you think of as points in Rn, and the right-hand side you think of as the tangent space to Rn, as vectors in Rn. Okay, so it takes points to vectors. That is a vector field in Rn. Now it's just a map from Rn to Rn. So we can differentiate this in any direction. So given a vector v in Rn, you define what's called the covariant derivative of y in the direction v. So it's just the usual directional derivative, nabla sub v of y. So this is the derivative of y along the straight line in the direction v. So this is limit t tending to 0, y of p plus tv minus yp divided by t. Okay. So if I think of y as a map from Rn to Rn, then I know what this is. This is nothing but the derivative dy at p applied to the vector v. Okay, y is a smooth vector field, I'm assuming. And then if I have two vector fields x and y on Rn, two smooth vector fields, I can define what's called the covariant derivative of y with respect to x, nabla xy. So this will be the vector field on Rn given by, at each point p, nabla xy at p is, you differentiate, you take the directional derivative of y in the direction xp. Okay, so it's nabla sub xp of y. So, all right, so this is the covariant derivative in Rn. It's just the usual directional derivative of a map from Rn to Rn, a smooth map from Rn to Rn. Okay. Now, this covariant derivative, it satisfies some nice properties. So the first is again a Leibniz rule, a product rule. When I look at how it acts with respect to the inner product of two vector fields. So So there's only 1 minute left in this meeting. So let me stop for now. We'll rejoin after the 1 minute passes. But is there any question you can ask in this 1 minute? Any question? Okay, so let's just wait for this to finish and then we'll join again after this finishes.